Hello, everyone, and welcome back. This is the final video in this series on single variable real analysis. And what we're going to focus on here is Newton's method. This is a root finding procedure that can be implemented with a simple for loop in any programming language that you might be familiar with. Now, I'm going to take a more analytical approach to Newton's method today. We're going to prove that it converges under certain conditions. And the awesome thing about Newton's method is that it's going to incorporate a lot of the things that we've talked about over this lecture series. In particular, the proof is going to rely on things like the intermediate value theorem and Rolle's theorem and Taylor's theorem. And I'm going to apply it after I give you the theorem to show how we can create a sequence that converges to the square root of 2. And if you go all the way back to when we started talking about the square root of 2 and sequences that converge to it, you'll notice that the sequences I was constructing there were very, very hard to construct. At least they took a little bit more thinking. Whereas the sequence I'm going to show you today can be implemented, like I said, with a simple for loop in any sort of programming language, maybe Python or MATLAB or Java or whatever it is that you like to use. And it can give you a sequence that converges to the square root of 2 very, very, very quickly. So up to some precision that you define. Okay, so what we're going to do is I'm going to start by telling you the basic concepts of how Newton's method works. Then I'm going to give you a theorem that tells you exactly when we can guarantee it converges to the root that we're interested in. And then we'll start talking about the square root of 2 again. So let's jump right into it. Okay, so the basic idea here is that I have some function. It doesn't really matter what it looks like. But let's imagine that it has some root that I'm interested in finding the value of. And so one thing that we've seen over the course of this course is that root finding procedures are not, or finding the root of a function is not limited to just saying where's a function 0, right? A lot of our proofs rely on the fact that we're interested in finding roots very, very abstractly. They have meaning outside of just saying, where is a function 0. So this can be thought of as a very, very abstract procedure that is applicable to a wide range of problems over mathematics. Now, you imagine you have some function and you know that there is a root r. So maybe you can prove its existence using something like the intermediate value theorem. Now, here's the other issue. Maybe you don't know what it is. You just know it exists, right? That's what most of our mathematical proofs tell us. They say there exists, but it doesn't tell you how to find it a lot of the time. Okay, so imagine I'm not very good at this, and I take a wild guess, and I say, okay, well, I know maybe my guess at the root is some point. I'm going to call it x1. Okay, and the question is, well, if I trace this up to the function, I get something. Maybe if this is super zoomed in, I get the point f of x1, which maybe is close to 0, but it's not quite 0, right? Again, if you really, really zoom in on this, I'm sort of exaggerating this so it looks, it's easier to draw. Okay, so I didn't get it right on the nail, or I didn't get the nail right on the head here. So the question is, how do I update my guess? Well, here's what I want to do. I want to find a line, let's put it in yellow, that will be tangent to the point x1 comma f of x1 and intersects with the x-axis. So I'm going to do my best to draw this thing. This is my line right here, and you can do some computations. The equation for this line is y is equal to f of x1 and then plus f prime of x1, that's the slope, x minus x1. Okay, then the question is, so this is just the tangent line. The question is, where does this thing hit the x-axis? Because if you just look at my picture here, wherever that thing hits the x-axis looks like a much better guess for the root, right? My original guess was x1, but you can see that if I call this thing x2, then just by tracing where that tangent line goes down to the x-axis, clearly I've got a much better guess if I update myself by just finding this value of x2. Well, that is as simple as just saying when does y equal to 0 on this line? And so you can get an update where you can define x2 by x1 minus f of x1 over f prime of x1. So all I did was took that equation of the tangent above, set it equal to 0, and just solve for the value of x, which I called x2. Okay, well then, let's take a look at this. It's going to get messy very, very quickly, so I'm not going to draw too much more on here. But you can see that if I repeated this procedure and found another line that's tangent, I'm going to jump to a better guess again, right? So I get some other point here, we call it x3, and x2 allows me to update to go to x3. So the general procedure, well, that is that if I give you some guess, call it xn, I can tell you what a better guess is going to be, at least just based on my picture so far, that xn plus 1, the next element of my sequence, is going to be the previous value of xn minus f at xn divided by f prime at xn. Right? So this gives a sequence, something that we are very, very familiar with now, a sequence xn, and hopefully, so maybe I'll just put this in brackets, hopefully we have that xn converges to R. So essentially what's happening here is you're approximating the root. You're getting better and better. You're getting closer and closer, right? That's what convergence really tells us. So, assuming this procedure actually works, this is allowing us to lift a lot of the abstract ideas that we've talked about over the course of this class, especially sequences that have been the core foundation of the class. And this allows us to generate sequences that converge to roots of a function. It doesn't have to be a polynomial. It could be any function you want, right? Very, very abstract, as long as I can take a derivative. And like I said, you can generate this sequence on a computer, right? If I know xn, then I can get xn plus 1. It's an inductive procedure that I just keep stepping forward to generate the sequence that eventually gives better and better approximations of my root. Now, this root finding procedure is known as Newton's method. And yes, that is Isaac Newton, the sort of inventor of calculus. So another thing with his name on it that is calculus related. And in particular, we have a theorem that tells us when Newton's method is actually going to converge. So let's go ahead and write down the technical details here. We'll prove it, and then we'll talk about an application. So let's let I be an interval, say a to b, and let f be a function from I into the real numbers. And we're going to assume that this thing is twice differentiable. So if we use the notation from the previous lecture, that means f is in c to the power of 2 of I on the interval I. Let's suppose further. So suppose f of a times f of b is less than 0. That means that they have different signs. One is above 0, one is below 0. And since this thing is continuous, the intermediate value theorem tells us there has to be a root. But before that, let's assume that there exists little m and capital M such that, well, the absolute value of the derivative of f is bounded below by m, which is a positive number. So what this is saying is that the derivative is never 0. There's no sort of turnaround points here. And the second derivative is just bounded. And this happens for all x and I. And we're going to let capital K equal to capital M divided by 2 little m. Okay, so these are all my assumptions. They actually looks like a lot, but it's fairly standard, right? It's just assuming that I have a root and that my sequence doesn't, or that my function doesn't really turn around in between here. Well, then there exists a subinterval. So a subinterval, which I'll call I star, which is contained in I, which contains, so containing a root or a zero, which I'll call R again, of F. And then such that for all initial guesses that you choose in this subinterval, the sequence xn defined by the Newton update. So that is xn plus 1 is equal to xn minus f of xn divided by f prime of xn. And this is for all natural numbers, of course. Well, every single element of that sequence belongs to the subinterval. So belongs to I star. And xn converges to your root. Moreover, we can talk about how quickly we converge, and we'll come back to this. This tells us that xn plus 1, it's the distance of xn plus 1 to the root is less than or equal to some constant times the distance of the previous step to the root squared for all n and n. Okay, so that's a lot to digest, right? Half of that is just giving you the assumptions here. But then what does this actually say? It says that there is a whole subinterval inside of your original interval that if you pick initial guesses from, you are going to guarantee that you converge to the root. In particular, that root is unique, right? We're going to prove that right off the bat. And that tells you all you need to do is have a good initial guess, right? Essentially, it just says if you want to do this computationally, you just need to start close enough to the root. You don't need to know exactly what the root is. You just need to start close. And then you have a guarantee, as long as you can satisfy the assumptions here, that you are actually going to converge to the root. And the last piece of this at the bottom tells you that you actually have quadratic convergence. So, whatever the distance of your previous step, xn, is to your root, say it's 0.1 or something like that, then xn plus 1 is going to be the square of that distance, right? So if you take a small number and square it, it gets even smaller. So this is a quadratic convergence result. It's very, very, very quick. We'll come back to that in a moment, but let's go ahead and look at the proof here. So the first thing we're going to do, we're going to prove that the root's unique. And this is going to use a lot of the techniques and ideas that we've fleshed out over the course of this class. So since f of a times f of b is less than 0, one is positive, one is negative, these things have opposite signs. And by the intermediate value theorem, there exists R between A and B such that f of R is equal to 0. Okay. Moreover, by Rolle's theorem, R is unique. Now, why is it that I was able to say that R is unique? Well, here's how the argument's going to go. I'm going to say it out loud. I want you to try and fill in the details and use Rolle's theorem here. So imagine there's a second root, call it S or something. That means that you have two values, f of R and f of S, that are equal to 0. Rolle's theorem tells you somewhere in between those things, the derivative is 0. But if you look at my assumptions here, I've assumed that the derivative can never be 0, right? F prime of x, I'll just underline it, f prime of x is bounded away from 0 on the entire interval, which contradicts what Rolle's theorem gives us, which tells us we have to have a unique root. Okay, so this is how we can use Rolle's theorem to tell us that we have unique roots of functions. Okay, let's now proceed. Let's start actually looking at the sequence that's generated. So we now let's call it just x prime be an element of my interval, be arbitrary. We're going to do this for every single element of the interval. So by Taylor's theorem, again, now I know that I've got a root. Well, there exists some mu between x prime and r such that, well, remember 0 is equal to f of r, and we're going to expand around x prime. So this gives me f of x prime, and then plus f prime of x prime, r minus x prime, and then plus 1/2 f double prime of mu r minus x prime squared. So if you're really paying attention here, you can probably see where that quadratic convergence is coming from, right? Because we can kind of see it already showing up from Taylor's theorem. Now, here's what I want to do. I want to take this and I want to kick it over onto the other side. So that'll be my first step here. So I get minus f of x prime, and this is equal to, now just putting down everything that I had before that's left. So remember, we can do this Taylor's theorem argument because we have twice differentiability, right? F is in C2. Now, if x double prime is such that it's the Newton update, so it's x prime minus f of x prime divided by f prime of x prime. So I'm avoiding using x1 and x2 because I am trying to be unspecific right now. I'm trying to say, you know, no matter what your initial guess is, here's what you're going to get. So I don't want to have to say, you know, it works for x1 and x2, then it also works for x2 and x3, and then x3 and x4. I'm trying to just keep it very, very, very general. So if x double prime is the Newton update here, according to this Newton method procedure, then let's call this star, maybe, just so I can reference it. Well, then if you divide off f prime from every single term here, then on the left-hand side, this becomes, well, I get x double prime minus x prime, and then plus, is equal to r minus x prime, and then plus 1/2 f double prime of mu divided by f prime of x prime, and then r minus x prime all squared, right? So all I did is I divided off the f prime term. I got on the left-hand side, negative f of x divided by f prime of x prime, and that can be, using the Newton step, that's the same as x double prime minus x prime. Okay, now I've got a negative x prime on both sides, so I can cancel them out. And now I can say that x double prime minus r, so this is asking how far away my update is from the root. Well, this thing is 1/2 f double prime of mu divided by f prime of x prime, and then r minus x prime all squared. Okay, what do we do now? Well, now we can slap some absolute values around this thing. So I get x double prime minus r, the distance now. This is less than or equal to, now let's all put this here, 1/2 f double prime of mu divided by f prime of x prime, and then, r minus x prime squared. This is still equal, actually. Now I can use my bounds on the first and second derivatives for f to actually see that this is less than or equal to k, where k was defined in the statement of the theorem, times x squared. So that's my quadratic update, all right? That is exactly that piece that's underlined in red. That's what we've just proven, that the distance of your update in the Newton step from the root is at most k times the square of the previous step. Okay, but we still haven't shown that we have convergence, right? So now what we need to do is we need to be strategic about where we pick our initial guess from. So we now choose, well, we're going to choose a delta smaller than 1 over k, such that the interval, well, this interval, this is going to be my I star interval, my sub interval. This is going to be a delta neighborhood of the root. So I'm moving delta away. And this thing still has to be contained in I. Okay, so the constraints on delta are twofold. First of all, it's smaller than 1 over k, and it's small enough that I have wiggle room to stay inside of my interval. Now remember, this is always possible because my root r is strictly inside of my interval. It's strictly between a and b, and that's again by the assumptions on this this theorem, this Newton's method here. So it's in the interior. There's wiggle room, right? Okay. Now, if xn, a current iterate, is in this subinterval, then by definition, the distance of xn to the root is less than or equal to delta, right? Because it's in this delta neighborhood of R. That's the definition of I star. And so then the next update, well, we already proved that this is going to be k times the original distance squared, which is less than or equal to k times delta squared, which, since delta is less than 1 over k, this thing becomes less than delta, which implies that xn plus 1 is also in the small interval or the subinterval I star. So what this tells you is that if you pick an element in the subinterval I star, then its Newton update, xn plus 1, is also going to be in there. So therefore, let's start a new page. Therefore, by induction, if you choose an initial guess in the subinterval, then every single element of the sequence generated by Newton's procedure is in that subinterval as well. That's what it tells you, right? That sort of, you can imagine that subinterval is sort of trapping you in there. You're stuck. Okay. Well, then also by induction, so I'm going to leave this, the full proof of this to you, but I'm going to write down what this is. I want you to think about it. I want you to try and see exactly why I'm saying this. We have xn plus 1 minus r. Well, this can actually be written as k times delta to the n, and then the distance of your initial guess, x1 to r. And let's take a look at this. K times delta is less than 1, which implies that if you take powers of it, this goes to 0 as n goes to infinity, right? I think we proved that on the second day. So this is also positive for what it's worth. But again, this is just a geometric series. I'm just multiplying in k times delta each time. Since it's smaller than 1, this thing's going to go to 0. And the distance from x1 to r, well, that's independent of n. That's just a constant. So this implies that xn converges to r as n goes to infinity. Boom, there it is. We proved it, right? So what this actually says is that if you get a good enough initial guess for a non-degenerate root of this function, then you are going to converge to that root. Okay, so again, think about what the proof is actually used. Let's go through the checklist here for a second. Here, intermediate value theorem. That's great. We covered that. Rolle's theorem. That's great. We covered that. Taylor's theorem. That's great. We covered that, right? The interior of an interval. Great, we covered that. We have this piece right here, right? These geometric series. Great, we covered that, right? So think about how much work, over the course of the semester just has been used for this one theorem. And as I promised at the beginning of this, I said we can use this to find the square root of 2. Actually, you can use this to find the square root of 3, 5, 8, any number you want, 51, 1,623,000, whatever. I don't want to accidentally pick a square there, but you can use this procedure to easily approximate square roots. So we can use Newton's method to approximate the square root of 2. How do we do this? Well, we just need to find a function whose root is the square root of 2. So let's let f of x equal to x squared minus 2. There are lots of choices, but this is a really, really nice one. Super easy. There's only 2 roots to this function, square root of 2 and negative square root of 2. So you can do the same thing. You can do a Newton's procedure to find the negative square root of 2 as well. Now so we note f of the square root of 2 is equal to 0, and f prime of x is equal to 2x, which does not equal to 0 for all x not equal to 0. So what this is essentially telling us in the context of the previous theorem is that you have a separation at x equal to 0. And essentially, you should understand what's going to happen here. If you start with a negative initial guess, it's going to converge into the negative square root of 2. Whereas if you start with a positive initial guess, it'll converge to the positive square root of 2. That's why we have to avoid these turnaround points, right? So my interval, whatever I want to use to actually apply the theorem, is going to just be composed of positive numbers, right? I cannot include 0 because that's the sort of splitting point. You can think of that as the top of the mountain, right? You can either roll left or roll right, but you could actually perfectly balance right at the top of the mountain, which is at x equal to 0, where you're not going to go left or right at all. Now, the nice thing about Newton's method in practice is that you don't have to actually think about what the interval is a lot of the time. So let's first see what the procedure is. So we have xn plus 1 is equal to xn minus f of xn divided by f prime of xn. And let's actually put this together. This tells me after putting in f and f prime, I'm going to simplify it so it looks nice. I get xn and then plus 2 over xn. Okay, so this is my Newton procedure here. After I do a little bit of cleaning this thing up, right? So you can do that. You can put in f and f prime and make it look pretty. Okay, so now let's think about this. What do I want to use for an initial guess? Well, like I said, pretty much anything positive. So maybe I'm really, really bad at figuring out what the square root of 2 is. Let's take x1 equal to 1. So, you asked me what's the square root of 2? I said, I don't know. I think it's like close to 1. I don't know what it is, right? Maybe I've never seen the square root of 2 before. So I said, it should be close to 1. So that's what I'm going to use my initial guess. Well, then if you want to undertake this procedure, you can just put x1 into this sequence to get x2. Well, then x2 gives you 3 over 2, which is 1.5. Okay, so that's a lot better, right? If you think about what the square root of 2 is, it's like 1.414. So, we're much closer. We've jumped to the other side, but we've gotten a lot better. This is a much better approximation already. Okay, then imagine I put in 1.5 as my guess. The question is, what do I get next? Well, in this case, I get 17 over 12, which is like 1.41666, and then lots of repetition, right? But look what happened here, right? 1.5 was off by 0.1 at least, right? Because square root of 2, I'll just remind you, something like 1.4 0.414, blah, blah, blah. So, I was off by the first decimal place, but now take a look at what's happened. I've got 2 decimal places of accuracy here. That's pretty good, right? All I've done is 2 steps. Think about how little computational programming power that I've had to use here. Almost nothing, right? Very little brain power too. And I've already got a 2-digit approximation. That's the quadratic convergence of Newton's method at work. So if I keep going, x4 is going to give me, let's say, approximately 1.414. All right, we've got at least 3 decimal places. Actually, we've got 4. Blah, 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 right? And I'm going to give you one more just for the sake of it. But after about 5 iterations, we have actually 11 digits of accuracy here. So 1.41421356237 blah, blah, blah. And the question is, maybe you're asking yourself, Jason, how do you know that I actually have 11 digits of accuracy if I don't actually know what the square root of 2 is? Well, if you do x6, then you'll see that the first 11 digits don't change. That's essentially how I'm determining if I have how much accuracy I have. And so, you can keep going on this procedure and imagine you want to get 100 digits of accuracy. Easy, right? It's probably only going to take you maybe 10 or 20 iterates of this thing, which again, if you think about how to do this on a computer, 10, 20 iterates of a for loop is nothing, right? That is something a computer can do in 2 seconds flat, not even. Even just doing this by hand wasn't even that hard, right? It's mostly just a little bit of arithmetic. Maybe I needed a calculator, but that's okay, right? It's not so bad. It's really, really, really nice. And again, you can do the same thing. You want to do the square root of 3. Well, just replace x squared minus 2 with x squared minus 3. You want to do the square root of 5, x squared minus 5. You can do all kinds of these procedures by approximating numbers that are irrational just by posing them as roots of potentially polynomial functions to keep your life simple. All right, let me close with some remarks here, right? So the first thing I want you to see is this quadratic convergence. So if we let En be the error, so E stands for error here, and this is the error in approximating the root at each step, well then, we can actually say that if we multiply by k on each side, I'll show you where this comes from in a moment, this is less than or equal to k e to the n squared. Now, where did I actually get that inequality from? Well, that's from Newton's method, right? That's the thing that's underlined in red here. The only thing that I did is I multiplied both sides by k so that I could put the right-hand k in the square with the En error, right? So this is En, this is En plus 1. And so essentially the k just comes as a scaling constant for the error, right? So if k is really, really big, it's gonna take a while for us to converge, and we're going to need a very, very good initial guess. Whereas if k is super, super small, then we can see that you can do really bad initial guesses and still converge quite nicely. Now, consequently, this quadratic convergence tells us that, if k times En is less than, say, 10 to the minus m, so you have m digits of accuracy, for example, in this error term, then, well, what the update tells you is that k times the error at the next step has double the number of digits in accuracy. Now you have to be careful, right? The k is in there scaling it, right? This isn't the error. It is the error relative to the size of k. That's what's happening here. But that is quite the jump, right? If you have 4 digits of accuracy, the next step is going to give you 8. If you have 8 digits of accuracy, the next step is going to give you 16 digits of accuracy. That is awesome, right? And that's what we were seeing happen right here with this convergence to the square root of 2. I already got 11 digits of accuracy after just 4 iterations going up to x5. And think about how bad my initial guess was, right? I was off by 0.4 or 0.41, right? I was off by a lot. but I still got really, really nice convergence. Now, another piece of this is things can go wrong, right? So be careful. There are situations where this can break down. And let me show you two of them. Okay, so imagine I'm going to start with a really bad initial guess. Okay, so here's my function. Maybe it just sort of asymptotes over to the right. And this is my function that looks like this, right? Now, the theorem tells you that there exists a subinterval, some initial set of initial guesses that are going to converge into R, but it doesn't tell you how big it's going to be unless you actually get under the hood and calculate out what K is, right? Now, if you just did this on a computer and you took some wild guesses, things are, if you just pick a really bad initial guess, things could go very, very wrong for you. So for example, if I pick X1 over here, then if I follow this up, what's going to happen? Well, if I generate my Newton sequence, I get X2 right here, and then I get X3 way over here, and more and more and more. And essentially what you're finding is that Xn goes to infinity. And what's the issue with this? Well, we went too far away, right? This is f prime of x is equal to 0. So if we were going to use this x1, then it would have had to be in the subinterval. And that subinterval also has to include R. And by assumption from the Newton, from the theorem, we cannot have a zero derivative inside of that interval. So that's what we're violating in this case. All right, let me show you another case where things can go very terribly wrong. Imagine I've got a function that looks like this. Okay, so the specifics of the function aren't that necessary. Again, here is my root that I might be interested in. And this is my x right here. Okay, well, imagine, this isn't drawn perfectly, but imagine I use, say, x1. Actually, I need to erase this and make it look a little nicer. It needs to have more of a slope to it. So if I choose my x1 right here, this is my x1, then what's going to happen? Now, if this was drawn nicer, I would jump over down to here, and I would get x2. And then again, if it was drawn with better slope, I would jump back up and I would just get x1 going to x2, going to x1, right? And I would just get this alternating sequence. I apologize, the drawing isn't the best, but you can come up with these examples very, very nicely. And what's happening here is that essentially what you've done is you started way too far away from your root, right? So you're outside of the subinterval, right? So then you have actually that these k times delta term is actually bigger than 1. And so you don't actually necessarily have convergence here, or bigger than or equal to 1. And so therefore, you can't guarantee that you have convergence. Now, again, I sort of apologize for the picture, right? I'm not the greatest drawer, but I want you to really sort of think about where these things could potentially go wrong and how you can circumvent this, right? Sometimes for Newton's method, you need very, 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 very accurate initial guesses. Otherwise, the theorem isn't going to apply and you can't guarantee that you have convergence. Okay, we made it. So thank you very much for sticking with me. This has been an absolute pleasure of mine. I hope that you've enjoyed it as we've gone through. And in particular, I hope that you've enjoyed this lecture. Newton's method is one of my favorite things in all of mathematics. I think it's super interesting. And it's, as I've shown you over the course of this lecture, it unites a lot of ideas. And really, it's a good litmus test for how we can approach higher level and more abstract problems in mathematics, right? So we've learned all of these properties of functions and sequences over the class of this or over the course of this class, and some of them feel very, very abstract and intangible. And so the purpose of presenting Newton's method today is to show you how these things can be used in practice and how they can help us with actual problems, actual computational problems, right? Remember that I actually need to know what the square root of 2 is, at least approximate it, because I use it on my calculator all the time. So of course, generating a sequence that can approximate it to any accuracy is a good thing to have. And so similarly, as we progress through mathematics, we get more and more complicated results that rely on many of the sort of simpler ideas that felt like they might have been useless over the course of this class. So this is just a stepping stone, and I hope that this has been helpful for you, and I hope that you carry some of these ideas forward and that they are beneficial to you in the future.